wanted to say from the very beginning that the idea of this talk was to give some kind of semi-educational presentation. Also, I mean, for those who are new to the field or who are outside of the field. But as I can see in the audience here, I think that the majority of the people actually know some of that, if not everything, which I'm going to say. But so I still hope that I will be able to make some comments which are not contained in standard literature about this. But on the other hand, I will of course go through all these things. I mean, in order to make an attempt to present more or less a consistent view on the origin of various molecular theories which are used in practice. And also, this wouldn't be very consistent because, in fact, the theories, at least some of them are not, even though I'm using them myself every day. So that's not kind of a presentation with results. I mean, this is a kind of philosophical talk or semi-philosophical talk where we describe what we're doing in general. Yeah, and so, we can start. So imagine that there is somebody outside the field who may have various, too elevated expectations about the theory of liquid crystals, and in particular about the molecular theory of liquid crystals, because people may naively think that molecular theories are somehow derived in a nice way from first principles, and the derivation is undertaken in the controlled way, so we know the limits of applicability and where it can be used, where it cannot, and things like that. And then we know that there are different nice approximations which are used in different contexts and so on. But in fact, this is not the case, or at least not really. And this has a very old history, actually, not related to the molecular theory of liquid crystals themselves, but to the molecular theory of fluids, or liquids. Because here I put the quote of Landau, that there is no such thing as theory of liquids. Because Landau was very much opposed to the theory of liquids. Because, as you may know, the Landau school was organized kind of as a religious order. And so that, because I experienced that in my youth. And within this order, it was not allowed to quote molecular theory. So there was a lot of debate, say, between Landau, Frankel, and other people, Boголюбов, who were developing this theory. And there was an alternative school at that time in the Soviet Union, and this was the school of Boголюбов, of course, who was doing the molecular theory. And for example, you may notice that in the standard sequence of books, theoretical course of Landau and Lifshitz, in the original edition, there is no volume about theory of fluids, and there is no volume about kinetics, because Landau also didn't believe in kinetics. He also thought that kinetics doesn't exist, and that's why he missed, for example, such things like fluctuation dissipation theorem, developed by Kuber, Cullen, and others. But because the school was very powerful, so it was actually predominant. And I remember that when I was a PhD student, some of my colleagues from this school, they were teaching me that the only thing which you're allowed to do from the molecular point of view is to estimate coefficients in the Landau theory. So, using dimensional analysis. And of course, this sometimes works. But for example, I will not do this in detail, but it's known that in liquid crystals, this normally doesn't work. So with some limited success, you can estimate the elastic constants in this way, even though you make a mistake by order of magnitude, but that's not much. But if you try to estimate, for example, the anchoring energy, and in fact, if you look in one of the old papers of Dejean, there is this kind of estimate. But at that time, not much experimental data were available. Here you make a mistake of 3 orders of magnitude. So in other words, from such a dimensional analysis, you assume that director is fixed by nails at any surface. And so a weak anchoring simply doesn't exist. And so on and so forth. So as I say, that this is a very long story, because all these inconsistencies, too much intuition in derivation and things like that, they could not attract the people from the Landau school or similar kind of theorists. So up to now, there are two different schools, I mean, who prefer different approaches. But because I am somehow originating, although indirectly, from Bogolyubov's school, so I, of course, like this also from the, not because it is very rigorous, but because it gives me an insight. So at least I think it gives me some insight into a more interesting physics of this. So that's why I am doing this, and that's why, but on the other hand, I'm quite conscious about limitations of all that, and I understand that none of the molecular theories should be taken too seriously. And so I'm going just to illustrate using some examples. Why is this? So before discussing some particular approaches, let me give you some general introduction, because I think even though some particular details were mentioned in previous talks, but I would like just to summarize this general idea about where the density functional theory is coming from, why we need density functionals, and what is the thermodynamic origin of all that. Because that's quite interesting from my point of view, even though that's a very general material. So let me start with the following things. So in thermodynamics, there are two types of potentials, which are historically called the Gibbs and Helmholtz thermodynamic potentials, although names are not important here. And the classical example, so do I have a stick? Yeah, I do have a stick. Yeah, the classical example is if we consider the potentials which depend either on volume or pressure of a fluid. And in this case, so that's a Gibbs potential which depends on temperature, say, and volume. And this is Helmholtz potential which depends on pressure and temperature. And they are related by this Legendre transformation. So we add this term P dot V, which always has the dimension of energy. That's an important. That if we have conjugated variables like pressure and volume, then they can be conjugated thermodynamic variables only if their product has the meaning of work or of energy. And in case of pressure and volume, that's the case. And now we can understand the left-hand side of it in the following way. So we understand that this is something which depends on V. On the other hand, in the right-hand side, the potential depends on P. So V here is obtained by minimization of this. And so you use this formula that P is to be the derivative dF by dV. And that's the simple essence of the Legendre transformation in this context, the simplest possible one, of course. And in fact, again, every theorist in liquid crystals uses this.
I'm sorry,
yeah.
Minus sign, right?
Yeah, I think it's minus, yeah.
No, P is minus dF.
Yeah, sorry. Because when you minimize it and when you move. Yeah, so, but then...
Also, the minus P. So it's consistent.
Yes, and so there is also the pair of electric field and polarization, and which is now already closer to what we're doing. So we can consider, for example, potential which depends on electric field, and this is our external variable. So now now we try to distinguish between external and internal variables. So what variable we call the external? The external variable is normally the variable which is present in the Hamiltonian of the system. Like, for example, we can write an interaction energy between molecules and then say molecules with the electric field. And so electric field is then the external variable. And then the conjugated variable, which is polarization, is the internal variable. And so strictly speaking, Hamiltonian doesn't depend on polarization. And moreover, these internal variables, they play a crucial role in the theory of phase transitions because symmetry breaking occurs with respect to internal variables. So, for example, if we have a paraelectric ferroelectric transition, it may occur at zero field, for example, and then we may ask what is P in the case of zero field, and P depends on in which phase we are, right? So if we are in the paraelectric phase, then P is zero, and if we are in the ferroelectric phase, then P appears self-consistently. So only internal variables may appear self-consistently, and this is deeply related to this symmetry breaking thing which is behind every phase transition. And of course we can now go to our Landau-Desgen expansion of the free energy, and here we have the internal parameter, which is Q tensor, in the simplest case. And obviously it can be zero or non-zero, as we understand, depending on the phase. And the external variable may be, for example, the tensor composed of the components of the magnetic field. So it is better than to use the electric field because there is no local field. But it's just, I mean, the formulas themselves here are not important. I just try to illustrate the principle. And so now it is interesting that if we try to develop any theory from first principles, then we need to start from somewhere. So we need some general formally exact expressions, right, which should follow from statistical mechanics. And it is interesting that we actually have such expressions only for Helmholtz type of potentials. So we only have the expressions for the potentials which depend on the external field. And so, for example, this is the well-known formula, I mean, for the free energy, right, in terms of the Hamiltonian of the system. And so here, Hamiltonian of the system will depend on what? It will depend on external fields, right, on electric field or on the magnetic field if it is present. And so only this type of thermodynamic potential is available. While what we want, if we want to use Landau expansion, then we want the potential which depends on the order parameter, Q. Right? If we want to develop a Maier-Saupe theory or Onsager theory or any other molecular theory of liquid crystal, we need a free energy which depends on the symmetry breaking variable. So on the order parameter, which is 0 in one phase and on 0 in the one phase. And the inherent difficulty of the molecular approach to the theory of phase transitions and fluids is then that we do not have a general formula which we can simplify in a consistent way. And then we need to do something with this. And here there are actually many different approaches, and most of them are intuitive. And this is the content of the molecular theory of liquid crystals. So the most powerful approach of this kind is the density functional theory, but fortunately Lech Longa has given here 2 seminars, and so I do not need to discuss in detail the derivation. So I will go very briefly over density functional theory and mainly outline those things which are important for this general derivation. But of course, I mean, thermodynamics is not so simple. We can't only think about external fields. There are other types of external and internal parameters. And the best example is the grand thermodynamical potential, where we have the pair chemical potential and the number of particles. Right? So again, this integral is written at fixed volume, right? Which means that in this case, and the fixed number of particles. And so we have a different formula for the grand thermodynamic potential, which will be on the next slide. And so again, there is less trivial, I mean, transformation between these 2 potentials. But actually, the density functional theory starts, and as I say, any molecular theory of liquid crystals starts when we try to express the free energy as the functional of the distribution function or generalized density, which we need then to describe different phases so that we can minimize this functional to find isotropic and isotropic solutions of different kind and so on. And in order to do this, I mean, one of the ways is to use this so-called generalized Legendre transformation, where we essentially just consider many simple Legendre transformations. So instead of taking the pair of conjugated variables, we can take many conjugated variables, for example, which would correspond to the density of species of a given orientation. Right? And because we can make not just one Legendre transformation, but a sequence of it. And thermodynamic potentials not only depend on electric field or polarization, but also on pressure, also on Q in nematic phases, also on number of particles, and so on and so forth. So there are several pairs. And so formally we can generalize it if we treat different particles located at different point and with different orientation as different species, and then generalize this to the following form. So that now there is a transformation between functionals. So one of them depends on this generalized density or the distribution function, and another depends on the generalized external field, which may generally include also chemical potential. But what is important, it depends on microscopic variables. So it depends on position and orientation. But all the rest is basically the same. So then in every molecular theory, we need to find this somehow. And then we need, either in this form or in simplified form, where it doesn't depend on the density explicitly, but may depend on the moments of density, which means on the order parameters. And then we need to minimize it to have a look where it has the minimum, and so on and so forth. And the problem always is that we can relatively easily write an approximation for that. And then we need to perform this transformation. There is no general way how to do this, at least I do not know. And the most general one is the density functional approach. But even there, I mean, many people have reservations. So I will. And so that's, again, I just, to save time, that's a quote from Lech Longa's seminar, because I just wanted to show that there is an explicit expression for the grand thermodynamical potential, which is rather similar to the Gibbs formula for the canonical potential, except for there is a sum over all number of particles. So this is the sum over partition functions of the systems which have different number of particles in this. But otherwise, I mean, the measure here is the same, so it is just exponent of the Hamiltonian. And then, in this case, we have this generalized external field, which is the difference between chemical potential and the real external field, which is supposed to act on every individual particle. And then the generalized density, in this case, which includes also real density and the density in the phase space, so orientational distribution function, is again just the variational derivative of this grand thermodynamic potential, and these two functions are the conjugated variables. And so then we can have this, again, this grand density functional. Because in principle, again, another thing which is rather complicated in the density functional approach is that you can use either the grand canonical ensemble or the canonical ensemble. This means that you can write down the free energy functional with fixed number of particles, fixed average density, or with variable number. Okay, so this was just, I mean, the general outlook, which shows that actually what we're doing and how this is placed in the general statistical mechanics and thermodynamics. But of course, now I would like to show you some simple things. I mean, because historically this has not been derived like that. So let me say a few words how historically the mean field theory has been derived and introduced, because that's also quite interesting from my point of view, because it shows how people intuitively were looking into that. So what is important to know that, of course, mean field theory has been known a century before Maier-Saupe theory has been developed, nearly a century. And it was developed in the context of crystals, so for lattice systems. And the simplest Hamiltonians, I mean, which we all know, are the Ising Hamiltonian or Heisenberg Hamiltonian. And so here, for example, we can write some simplest possible classical Ising-like Hamiltonian. So we have lattice sides, which are denoted by I and J. So we have, for simplicity, just a constant interaction between any two neighboring sides. So interaction is only between nearest neighbors for simplicity. And then the interaction is proportional to, so the interaction potential is separable in some way. So we have these coordinates, generalized coordinates xi, xj, which can be thought of, for example, the direction of the spin or deviation of the atom from the central position, and so on and so forth. And so this type of potentials are used in simple theories of ferroelectric crystals. And now how we introduce historically, I mean, the mean field potential. We just split the Hamiltonian in three parts. So we formally introduce the part which we call a fluctuation. So here the brackets mean the ensemble average of this x, which is the order parameter for this system. And so if we introduce this fluctuation, which is the product of the deviations of fluctuating x from the average x, and then if we want the right-hand side to be equal to the left-hand side, then we pick out two terms which are left here. And so one of them is the mean field potential. So one of them is the coupling between this microscopic variable and the average variable, which has the meaning of the average field created by all other molecules. But again, why this approach is nice, because we automatically get here the third term, which is not so obvious. And this is the energy of the mean field. And this term is quite important, because if we forget about it, because we can write all self-consistency equations without this term. But if we do not take this into account, then we can't minimize the free energy, because that's an important part in the free energy. And in this way, it is quite obvious where it comes from. And so then,
I'm sorry.
yes, you can of course
The
ask.
bracket, so your bracket here, the underlying probability distribution function with respect to which you're computing your ensemble averages, do you have a specific, that's to be determined, or you?
No, this is to be determined, because so far that's not a mean field theory. That's only the way how we split the Hamiltonian. And now in this naive thing, we will have to make various assumptions, so more assumptions. So for example, but because I think that people, are familiar with mean field theory more or less, so I'm not going into tiny details. But let me see. So what we formally do in the mean field approach, we neglect that. So we say that fluctuations are small, that their contribution to the free energy is not very important. There is absolutely no justification of that. And of course we know that that's incorrect in practically 100% of cases. But that's a simple approximation, and so we hope that we still capture qualitatively what is going on.
But you can check it afterwards, right? It might be, you guess that. but you
Yes,
check it
yes.
afterwards.
Yes, of course, and that's what we will do. We will collect more approximations. We will see that this is not as bad as you may think. Because when people first see this, they say, that's rubbish. It's absolutely complete.
Emission
Yeah.
J, of course, could be Jij.
No, yes, I just for simplicity put the same to simplify. Generally, of course, it can be Jij. It may depend on direction. And it may be beyond nearest neighbors.
Yeah.
So and that's actually is the case in most
And if
systems.
this is an Ising model, if this is an Ising model and X.
X, in the case of Ising model, X is a classical spin.
Right, so shouldn't the sign be different?
No, well, I can introduce the sign into J.
Oh, okay.
Yeah, because in this case J is negative, so you can explicitly write it
Okay.
negative, or you can...
It could be an angular variable or
Okay.
Yeah, so I just have in mind something simple like ferroelectric crystal, so that X is really the displacement, the positional displacement of the ion from a certain symmetric position in the unit cell, for example. Yes, and so now, so the next step, what we have to do is that we have to now to assume the form of the distribution function. Right, so if we have neglected this density. Now we always, in all approximations, we accept the Boltzmann distribution, right? So we say that n-particle distribution function is the exponent of our Hamiltonian divided by temperature. And because we have neglected this many-body term, of course, then the nth distribution function becomes the product of a single distribution functions. And this is just a constant, which doesn't affect it much. And so now we can immediately assume that, okay, now we have a distribution function, and we can just formally reproduce the Gibbs formula for this particular case. Again, this is, at this stage, this is intuitive. There is no proof that the free energy should be expressed in this way. So we simply copy the Gibbs formula for the one-particle case. So we write that this is logarithm of the partition function, and partition function is simply the integral of the exponent with a Hamiltonian in it, and this exponent is related to the one-particle distribution function. We just needed to divide it by the norm and to get that.
Sigma is the coordination number of the lattice.
Yes, yes. In this case, yes. Sigma, because we are talking about lattice, the number of nearest neighbors, yeah. And so then, of course, I mean, we need to check, I mean, that this free energy makes sense. Right, and in order to check this, we need to check if it can be minimized with respect to the order parameter. Right, so this is a constant, so which goes out of the logarithm, and so we have this energy of the mean field, and then this reduced partition function. And then we can check that if we take the first variation of this free energy with respect to the order parameter, then we get the so-called self-consistency relationship. So that the average of x, the order parameter, is given by the average of this microscopic x with our selected distribution function. And again, historically, people didn't just derive that. They assumed this self-consistency equation, because this was the idea behind the mean field theory. That's why a mean field theory is sometimes called a self-consistent field theory, because this is called the self-consistency equation, the equation which enables one to determine the order parameter. So there may be zero solution or non-zero bifurcation at the second order phase transition, and so on. But of course, I mean, there are more sophisticated self-consistency equations, as we will see later on in the cluster approximation. So it's better to call this a mean field approximation, which is a particular case of the self-consistent one. Okay, so that's how you can do this on the lattice, and that's how people were doing this in the theory of magnetism in early 20th century.
Yeah, and of course one can actually directly minimize also this without having self-consistent equation and get numerical solutions.
Yeah, that's an important comment. I mean that when you only have self-consistency equations, you are forced to solve that, and you do not know which solution corresponds to minimum, which solution corresponds to maximum, without knowing explicitly the free energy. That's just impossible to answer this question. While if you have the free energy, you can, of course, minimize it. The problem is that, as Epifanio discussed this several times, I mean, that sometimes the free energy doesn't have a minimum in this approximation. But then still we can use self-consistency relationship, because they identify the stationary point, no matter whether it is minimum or maximum. And so, to a certain extent, if we know the general theoretical background, then we can just ignore the fact if it is minimum or maximum, surprisingly, and just obtain solutions from here. And that's what is very often done. Yeah, but this is a lattice, so we need to see if we can do this for a fluid. Right, and here the transition appears to be not so consistent, as we will see. So, in other words, I'm going to convince you that the mean field approximation is only consistent on a lattice. In fact, it is internally inconsistent in the case of fluids. And that's why it gave rise to other theories. And I will try to discuss that. But so far, let us see what we can do in the case of fluids. So we do not have a lattice, but we can then proceed more or less exactly in the same fashion, again, as Epifanio was recently describing. So let me repeat this briefly again. So we start with a pair potential, no say for molecules. They depend on orientation of the two molecules and on intermolecular vector. And then, because we say that we are doing the mean field potential, so the molecule should be subject to some average field, which created by all other molecules in the system. In this case, there are no nearest neighbors. That's the problem. Molecules can float anywhere. We need formally to take into account interaction between all molecules in the system. Yeah, but in the mean field approximation, the first thing we do, we assume that we can average this potential over all intermolecular vectors, just to integrate it. And in this case, we obtain the effective potential, which only depends on the orientation of the two molecules. And after this procedure, we immediately lose all positional correlations in the system. That's the first thing, which is a part of the mean field approximation. And then now we can say, okay, let us assume that the mean field potential, or effective one-particle potential acting on one particle, can be now obtained in the following way. So we take the molecules 1 and 2. Molecule 1 is fixed, and molecule 2 can fluctuate. But we now write the mean field potential as an average of this effective potential with the one-particle distribution for the molecule 2. And in this way, we just consider the semi-averaged potential. So the position and orientation of the second molecule is averaged, and the first molecule is sitting in this effective one-particle potential. That's more or less the same what we have done before, but we do not explicitly consider the fluctuation. And so we cannot actually nicely do this as nicely as before, unless we use a different approach. And now the second assumption is the same. So one particle distribution function is then Boltzmann function with this. Well, I think that I was too fast yesterday, so there is no integral, of course, here. It's just exponent. So sorry, there is no integral. It's just the exponent of this divided by z, which is the normalization constant. And then now we can write down the generalized self-consistency equation, for example, in the following way. So we can introduce a full set of orthogonal functions which correspond to a given symmetry of the phase, and then expand the mean field potential, which possesses the symmetry of the corresponding phase in terms of these functions, and then the averages of these functions will be the order parameters. And we can write a set of self-consistency equations for all these order parameters. So which will be a general form of the mean field approach. And then, of course, now, I mean, we all know how to do this in the case of liquid crystals. So we can, for simplicity, consider a nematic phase composed of uniaxial molecules. And then our potential depends only on unit vectors in the direction of long molecular axis. So when we average it over all intermolecular vectors, the resulting potential now depends only on the modulus of the distance and on the scalar product between these two unit vectors, which is a cosine of theta, angle between the two molecules. And now, because everything depends just on cosine theta, we use the Legendre polynomial expansion. So we take this effective potential and expand it in Legendre polynomials, keeping as many terms as we like. And we can consider polar phases, non-polar phases. So in the case of non-polar nematic, the first term is P2, which is non-polar. We can consider higher order terms and so on. Yeah, this is all very well known. And now there is one also interesting, mathematical remark here, that when we expand the effective potential, and then we need to substitute it into the expression for the mean field potential, which is the integral of this effective potential with the one particle distribution function. And what is very nice about Legendre polynomials is that they possess this nice property that when we integrate them with any function of the same variable coupled with any other vector, then we get the same Legendre polynomial, but instead of this microscopic variable which is integrated out, we have this other vector which stands in another. So the form of the Legendre polynomial is invariant under this transformation. And of course this is multiplied by some constant, and this constant is actually the order parameter. So it is the same Legendre polynomial integrated with this function. And so if this function is a distribution function, then we nicely obtain the expansion of the mean field potential in terms of order parameters, because this property is valid for any Legendre polynomial, not just for P2. So we expand effective potential in infinite series, we break it somewhere, substitute into the mean field, and immediately obtain the result as a sum of this type of terms. So interaction constant, order parameter, and the corresponding Legendre polynomial. So in this way we can generalize Maier-Saupe theory to higher order terms, which has been done ages ago, of course, and so on and so forth. And so if we just keep only one P2 term, then we obtain the Maier-Saupe theory. We obtain this distribution function in which we have only P2 term, and the Z is the one particle partition function. Yeah, again, that's the most well-known part in this business. But I would like to make a following remark. So, Maier-Saupe theory, which is essentially a composition of these two expressions, was extremely successful. And it is very simple, and it gives us a reasonable idea in the first approximation. Then there is a question why. Because obviously we have spoiled the system statistically in the most violent way we could. So it shouldn't work in principle. And now if we start to think why it works. So for example, in the original theory of Maier and Saupe, they used the model of the dispersion interaction. And in this case, this constant is proportional to the square of the anisotropy of polarizability of the molecule. And this is not right, because later on people synthesized liquid crystals with very low anisotropy of dielectric polarizability of an individual molecule, and they still form liquid crystals at about the same temperature, at least very often. Of course, everything depends on chemistry, but there are such examples. And so this was noticed long ago, so people realized that Maier-Saupe theory is very good, but the model is wrong. Anisotropic dispersion interactions do not seem to make predominant contribution. So later on, Gelbart with co-workers actually analyzed this using estimates. And they found out that predominant contribution is most likely isotropic attraction, on average, between molecules, modulated by an isotropic shape. And this gives you a right order of magnitude, and this is more or less a robust thing, valid for majority of anisotropic organic molecules. So again, Maier-Saupe theory works nice not because of the physics underlining it, but because of the P2 form of the potential, in fact. And then we will see that this P2 form of the potential has nothing to do with the mean field theory. So it is not because it is mean field theory, because it is the first term in the general expansion. And so it appears in any type of theory. That's the reason why Maier-Saupe theory works. But of course it doesn't work everywhere, so it gives a reasonable value for the order parameter. But for example, if you look into correlations specifically, and then you find enormous mistakes. For example, somebody mentioned already in the workshop that if you consider the difference between actual transition temperature and the bifurcation temperature, because this is a first order phase transition, there is a difference between the two temperatures. And this, the value of this difference is always estimated 30 times in there. So experimentally it is very small. And so physicists understand what is going on. If the two temperatures are very close, this means there are strong fluctuations in the highly ordered phase, so that they drive this temperature towards the actual transition temperature. And indeed, I mean, if you take in any simple way the fluctuations in the isotropic phase, for example, fluctuations of variables which are missing in this approach, then this difference decreases, and it decreases by order of magnitude in the cluster approximation. Okay, so now that's, I think we do not need this because it's still the Maier-Saupe theory. So, yeah. So now let us try to see how a mean field approximation can be derived in a more systematic way. So far this was a naive kind of approach, and now we will try to see if we can derive it more or less consistently. And this will be more or less consistently, not really consistently, because we have this general formula for the Gibbs free energy, which depends on the Hamiltonian, but we cannot use it because this is not a density functional. It can't depend on order parameters or on generalized density. So we make a trick. We say that free energy is generally the sum of energy and entropy, and this is known from thermodynamics. And now what is energy? Energy is, of course, the average of the Hamiltonian, right? It can't be anything else. And then there is an entropy, generalized Shannon expression for the entropy, where we put F log F, but we have here the full n-particle distribution function, which describes probability to find all molecules in a particular orientation and position, particular points in the phase space. And so now this looks like a density functional, right? Because it explicitly depends on the n-particle density here and here. In fact, this is a general density functional, even though it is not derived. We have just written it down intuitively. And it, of course, possesses the nice property that if we take a first variation of it, then we recover this Gibbs distribution function, right, which is the starting point for all statistical mechanics. So this should be correct. But, I mean, it's important to stress that we had to make a trick to get this free energy functional. But once we're here, we can now immediately derive mean field approximation. We just say that mean field is the approximation with no correlations. And statistically, this means that this n-particle distribution function can be factorized into the product of one-particle distribution function. So all correlation functions are zero. And Now we take this expression. Yeah, here x normally stands both for position and orientation of a particle. And now we simply take this expression as a product, substitute into here, and we immediately get the free energy in the mean field approximation.
Sorry, Misha, this Fi actually should be F. It is the same, isn't it?
Fi, yes, it should be F1.
F1.
Yeah, it should be F1, sorry, because I was doing this rather in a hurry, so as you see there are various types. Yeah, this is of course F1, the one particle theory, one particle distribution function. Yes, and so for example, when we substitute it here, you see logarithm becomes the sum of logarithms, then we integrate over everything except for Fi here, we get the mean field entropy, then this is factorized, we write H as a sum of pair interaction potentials, and again we integrate all extra distribution functions, and we get the mean field free energy. So we of course need to assume at this stage that we have pairwise interactions, and so then we, using this assumption and the mean field approximation, we obtain the general mean field free energy, which has more or less the same form as before, but it's more general because we can put any variables here, also positional ones. Right, so this functional can be used to describe transitions into semectics. And then if we formally minimize it, or more exactly if we take the first variation, because we're not sure whether it is minimum or not, yeah, then we obtain the general form for one particle distribution function, which has this mean field potential in it. Right, and the difference with the expression before is that we integrated distribution function may depend also on position. And in this case, we need to integrate over position, not just orientation, and we cannot introduce the effective interaction potential because it also depends on position. And this is the case in semectic phases, which are not translationally invariant. So there we cannot integrate the potential, and we need to use it in its full form. So mathematically, this means that we need to expand it in other type of, other nice set of functions, which are called spherical invariants. Again, they were mentioned during this workshop. Yeah, so I will not go into how it works, but in principle, this can be done. And then to do all kind of tricks here to derive the semectic theory. And so now there is this is the point where I'm going to say that this is inconsistent, generally, this procedure, in contrast to the lattices. Why? Because we have made an assumption that this integral exists.
But don't you need a density there, Misha?
Density where?
Dimensionally, the thing isn't right.
No, here
No,
there is a
below.
density. Hmm?
Line below.
Below, no, I am just defining it this way. So the effective potential is linear in density. So I think there is no density as far as I...
Is that as number density or?
Number density, yeah. I should...
The first integral is only an angular integral. So I think you're saying.
Yes,
you
so I
have the
mean,
row.
from dimensional point of view,
Yeah.
so this is 1 over volume.
Yeah, he wants just to have the row in the second line and not in the first line.
No, yeah, I can put it here if I want effective potential to have the dimension of energy. Yeah, I agree, this would be more consistent.
Is that what you had in mind?
I think so.
Yeah, so we can easily put it here,
absolutely,
yeah.
Yeah,
Yeah,
absolutely.
yeah, it doesn't matter, but for some reason historically it was not done like that. Although I agree that that's better, because you preserve the dimension. Yeah, but what I wanted to say here is that if we take any potential, so for example, Gay-Byrne potential, right, which explicitly depends on the intermolecular distance, and we substitute it into this definition of the effective potential, it all diverges, right, at some r, because these terms, they go to infinity, and they diverge strongly because of these powers of 12, 6, and so on. So essentially any potential would make this integral diverge at small distances. So there is something wrong about all that, which we didn't encounter when we considered the lattice models, because in the lattice models, molecules are well separated. So we can set some potential and nothing happens. But here they are free to move. And so when we made the assumption about absence of correlations, which is a definition of the mean field approximation, we actually have neglected a very important effect. And this is the so-called excluded volume effect, that the molecules have rigid cores, more or less. And so they cannot penetrate each other completely. Otherwise, indeed, the system would blow up. So there are electron clouds which repel each other, and so on and so forth. And so, in fact, we cannot access the region where this integral diverges. But we understand this physically, how we should stress this mathematically. Mathematically, this means that we have to give up our formal definition of the mean field approximation.
It's actually funny because you're absolutely right, but by a quirk of the Gay-Bern, if you take it down to zero, it becomes negative. So there is a repulsive barrier, right?
Yes.
And but if you were to do, for example, Monte Carlo, and should have steps which can take you over to very close distances, it's because it's just incorrectly written, it becomes negative.
It becomes negative.
In molecular dynamics, is not important because as the molecule approaches, they start
Yeah,
repelling. They never really.
They're repelled by this barrier.
I think Mike, you must have seen this as well.
This is true, yes, but it doesn't change.
No, it doesn't.
Yeah. No,
it's just a curiosity.
in real systems, we always have some probability, right, determined by the full Hamiltonian,
No, when they
which
are
makes states not equal.
artificially very
Right.
close,
And-
potentially is.
Yeah, so the practical way to overcome this difficulty is to say that there is a hard core. And so instead of the integral over R, we exclude some volume here. And everything bad happens within this volume. So outside this volume, everything is finite and nice. But this means that then we need to consider this hardcore repulsion, because we have done something to our approximation. We cannot continue to use the same free energy. That's the point. We need to prove that there is nothing else there. And in fact, there is something else. Once we have said A, we also need to set B in this case. And this B is the packing entropy. So if we look just at steric repulsion, so what is steric repulsion? So we can consider two molecules, right? And these are two spheres. And so the center of this sphere cannot penetrate into this big sphere, which is called the excluded volume for two spheres. And if particles are anisotropic, then the shape of the excluded volume depends on mutual orientation of the particle, right? So these centers describe some anisotropic volume, and if we change the orientation of this molecule with respect to the central one, then the shape will change. And so this excluded volume can be taken into account. So, for example, we can just forcefully redefine this effective interaction energy. So we do not simply integrate the pair potential, but we multiply it by e to the power minus u over kt, where u is the steric repulsion. And then we say that we consider extreme case, the infinitely strong repulsion, so that this potential goes to infinity. And in this case, this is just a step function. So the step function which cuts out everything, all states where when the molecules penetrate each other. And then we can replace this exponent by this step function. And this is now our new definition for the effective interaction potential. And so this constant psi is called the distance of minimum approach. And in some cases it can be derived analytically. So I have been very pleased to find in the BLCS conference that Fulvio derived analytical expression for hard sphere cylinders for this minimum distance of approach, which was not available before. So it can be used. Or maybe you know better whether it was known before, but it doesn't matter here very much. But as I say, that in principle this is a well-defined function, at least for concave bodies, which can be calculated at least numerically.
Michel, I
Yeah.
think you're absolutely right, this is a way out, but I think one can derive the equations consistently also for a potential that are a repulsive and an attractive part. And you could consider the Gay-Bern as having a repulsive and an attractive part, like many others. Then, going similarly to what you've done at the very beginning, when you introduce the separation variable, I mean, I did it in a very general way, but a long time ago. You can actually do it also for off lattice. In other words, you
Yeah,
get-
that's interesting, yeah, because now we are in the territory where we start to use
you
intuition,
get
right?
so it's,
Okay, I mean,
it's just carried away.
yeah, but
You get the potential as a sum of two, and then
Mhm.
the partition function would be e to the u, say 0 plus u1,
uh-huh.
and then by multiplying and dividing by the partition function u0, you basically write the total partition function as the unperturbed part, which could be the nicely behaving one, and the average of e to the minus u1.
That's like a cluster,
And then you do a
like a
cumulative
cluster
expansion, you
approximation,
do
yeah?
the- and-
But
and-
Okay,
and-
maybe-
It's saying,
maybe you can
it
say a few
eliminates
words
that. It's just
after
saying
that.
this
Because
is-
the
this is
integral
a
then,
possible.
no, but the integral then, I think, does not become the integral without a weight. The integral would be weighted by the repulsive part of the potential, which would be a way of doing this thing without invoking necessarily a hard core, but also with a well-behaved repulsive part that would keep your integral existing.
Yeah, this is very
We could work it
interesting.
out.
Yeah, so if you write the formula at the end, because I'm going to discuss this further.
Okay.
Yeah, I mean, the most interesting part is how to take into account simultaneously repulsion and attraction, and there is no unique answer for that. So I'm glad to hear that, if you can suggest something here, because I mean, there are possibilities, but no general way of doing this, I would say. So this is just a very, very intuitive and simple thing, which is not necessarily right or correct. It's just the way to avoid formal mathematical difficulties. And there is a price for that, of course. And so that now, that's just an obvious remark that this is no longer a mean field approximation. Because in this case, the Maier distribution function is not the product of two one-particle distribution functions, but it's multiplied by this step function, which kills it altogether at short distances. So this is the simplest correlation function, right? And so the physical meaning now of our procedure is that we have taken into account, in some very crude way, short-range steric correlations. And we have taken them into account where we cannot avoid that, because they're infinitely strong. Because when the particles can't penetrate each other, this is obviously a correlation between the position of the two particles, and moreover, that's an infinitely strong correlation. So at least it should be taken into account. So we need to do something like this, but as Claudio correctly says, there are many ways how we can do this. It's not the only way. And this is just a very, very primitive approximation for the Maier correlation function, and we can use more sophisticated ones in principle. Yes, but whatever we do, we have to consider then the so-called packing entropy. Because if we now use our free energy functional and only change the area of integration, introduce this step function, we are missing a term. Because as long as we changed our distribution function, then we understand that molecules cannot be anywhere. So we have changed the so-called packing entropy. Because packing entropy is the number of ways how you can put, say, your rigid bodies into a given volume. And because they cannot penetrate each other, so there is a restriction on their position. And as a result, packing entropy, so entropy doesn't like that. And so there is a penalty, and this penalty should be taken into account as an additional term here. And this penalty is actually everything which we have in the Onsager theory. And so, well, just naive description that the packing entropy is just some kind of the ratio of the excluded volume over all volumes summed over all particles. And in this case, you can express it as square of density and then the excluded volume. And if we have long rods, then we know that this packing entropy very much depends on orientation. So maximum of entropy corresponds to minimum of the excluded volume, and when the rods are parallel, then excluded volume reduces dramatically. And so there is a big change of this entropy at the transition. And so that's why it plays the dominant role in hard systems, and Onsager theory is based on that. And so if we just have a system of hard rods, there is no energy, the systems are thermal, and so we just have the free energy, roughly speaking, is the sum of two entropies. So the orientational entropy which depends on the orientational degrees of freedom, and the packing entropy, which is determined by the system of by the excluded volume, and then the balance between these two entropies is violated at the phase transition. So if we have a system of hard rods and we increase the number density, then we know that the system would undergo a transition into the ordered phase, and in the ordered phase the packing entropy wins, and in the disordered phase the orientational entropy wins, of course, because orientational entropy always promotes the disordered phase. And so this is just qualitatively the Onsager theory. And again, because I think Lech Longer, the title of seminar of Lech Longer was Density Functional Theory and Onsager Theory, and many people discussed Onsager Theory, so again I will not go into the details of it. I just say that, in fact, if to be more precise, the free energy is the sum of three types of entropy in this case. So packing entropy, orientational entropy, and mixing entropy. Because here we can vary rho, right? Because the transition in the system of hard rods is between two phases with different average density. And so we need to include rho as a variable here. And so this rho log rho is just the mixing, well-known mixing entropy.
Misha, I'm sorry to interrupt. You talked about the Shannon entropy. Now, when you come to the hard part, you don't have anything like that. On your first Onsager slide, you just had a sum over the excluded volume.
Yes, but I only consider this part. So this is the Shannon entropy.
Why no? Why don't you have a logarithm in the packing entropy just the same way?
Well, this is I would say that we can't answer this question before we can derive this consistently.
I agree.
Yeah, because so far what I'm writing is pure intuition, right? I mean, so Onsager theory is not a pure intuition, and so there we can really derive these terms. But if we go beyond Onsager approximation, then we can use this or that approximation depending on which one works better.
But this thing you're calling the Shannon entropy, that also comes out. I mean, there's a systematic zero expansion for the free energy.
Yes, that's what I'm.
But those last two terms are there.
Yes, I'm going just to describe why they're there, because that's also non-trivial, and Onsager was genius because he realized how to introduce it. Because you see, it's well known that it can formally be derived by the virial expansion. Palfi has described that, I mean. So we can start from the formal Gibbs free energy, which assume pairwise interaction, then replace this is the product of exponents containing different ij, different pairs. We can express this exponent as the product of the factors 1 plus the Maier function, where Maier function is this exponent which contains only one pair potential for two particles, -1. And then we assume that the system is very short range. And this is the case for repulsive interaction. And then this function is very short range, and when we have infinite integration here, or positional degrees of freedom, so we will always have to integrate this over intermolecular distance, and because of the short range character of it, this will be somehow proportional to the excluded volume, and it will always be normalized by the density to a certain power. And as a result, we can perform just a virial expansion in powers of volume fraction of these hard particles. And this will be just a systematic expansion, which is, the only question is whether it converges or not. And it has been shown that in the case of infinitely long rods it converges, because higher order virial coefficients, they decrease. So for spheres, for example, the virial coefficients are always some sort of sphere. All right, and so it's always proportional to the certain power of the diameter. But for rods it's not like that, because if you have three rods, then they make this configuration if they all touch each other. And so that's a very flat object. It's two dimensions are of the order of length, and one dimension is of the order of d. And this is becoming more pronounced when you consider higher order. So the series converges. But there is another problem in it. So if we formally do that, what I say, you put here, you make expansion, you do not get Onsager theory. You get a virial expansion just for this system, which is simply the sum of terms, virial coefficients and powers of density. This is not a density functional. There is no distribution function here. No generalized density, no order parameters, nothing. And again, we are facing the same problem because we have taken the wrong thermodynamic potential. We have taken Helmholtz free energy, which depends on external variables. And we do not know how to transform it into the Gibbs potential, which depends on generalized density. So in this way, that's impossible to do. And Onsager, as I say, he was a genius, so he realized how to bypass the problem. Because he actually has bypassed it in a very elegant way. So he didn't develop a density functional approach. But he said, okay, let us make the trick. Let us treat rods of different orientation as independent chemical species. And so then the distribution function is normalized, which would mean that the sum of these species is conserved. And so he just has developed this virial expansion for mixtures, for infinitely component mixture, where each component corresponds to a certain orientation. And in this case, we still have this mixing entropy. And we have many species, we have the sum of these mixing entropies. And then we take the continuous limit, and we get this entropy term, which we know from mean field theories. And now we have all these terms here, say in the quadratic, the second virial approximations. Again, we take the continuous limit, and we obtain the second contribution in the Onsager theory, which is just the integral with two distribution functions. So that's how it has been done by Onsager, and Onsager theory is the first consistent density functional. But it was derived and without using density functional theory. And moreover, in this case, I mean, that's why many people who work in the theory of fluids, they prefer to go no further than that. Because this is systematic. That's nice. You have a certain limit where it works. But if you start to violate this limit, if you consider short rods or you add attraction, then you are in the unexplored territory, sort of, where there are no consistent approximations. And here everyone has its own opinion about what to do. And so, yes, and so now we can generalize this in the following way. So, what is the simplest way to include both? So we start to discussing this. So we have packing entropy, orientational entropy, so this is Onsager theory, and then we want, for example, to include attraction. So the simplest way is to do this like it is done, I mean, that's the picture of an Egyptian god, which has the human body and the falcon head. Right, so it's the same thing. So we simply forcefully add attraction contribution, which we think should be of this form, to the Onsager theory. Of course, I mean, with this, with excluded volume, this is more or less consistent because we take excluded volume into account here. We account for the fact that it produces packing entropy. So qualitatively, this should be correct. And this is what is called generalized van der Waals theory. So there are several versions of it, but essentially it is like that. And that's the practical tool. So for example, if you open the paper which says that the use of density functional theory to determine this and that, most likely you will end up with this function. Because this is, yeah.
But this doesn't give you van der Waals equation of state.
No, no. And because, why it doesn't give you the van der Waals equation of state? Yeah, because, I mean, this is a too severe approximation here. Yeah, you're absolutely correct. There is no justification for that.
No, the energy part's okay. The packing entropy, I think.
Yes, and we will return to packing entropy. So packing entropy is also wrong because it is correct only in the limit of infinitely long rods. In the limit, it's correct. But if you want to derive van der Waals equation of state, you want spheres and not long rods. So you are in the opposite limit. And in the opposite limit, it has nothing to do with this expression, of course. And even in the intermediate limits. So then the question is that if you want to have infinitely long rods and add attraction, that if attraction is weak, maybe you can do it like this. But if you think that this can be done for not very long rods, so for realistic systems, then there is a question both here and here. Because obviously many people have made computer simulations and calculated the dependence of various properties on the length to breadth ratio for relatively short rods. Not very short, so even for 10 this doesn't work. quantitatively. But for 5,
Peter, what you're trying to say, I guess, given the talk that you gave last week, is that this doesn't have divergences at hard packing and things like that.
No,
yeah.
it's nothing
And
like
so now,
that.
because I'm not trying to convince you that I'm presenting you the theory of everything, it's just the overview of what is used in the theory of liquid crystals. So we may argue whether some of these things make sense, and I think that not all of them make sense. But I'm just describing more or less conventional approach, or some set of conventional approaches, which is used in dozens or maybe in hundreds of papers.
We're running a little over time.
Okay,
We'll
so
reach the end in 5 minutes.
yes. I think I will finish because we start to talk, so I will just
Yeah.
do this a little bit faster. Yeah, so because that's just a technical thing. So how we solve the problem for shorter rods? There is no solution. I mean, though the most popular way is the so-called Parsons-Lee approximation. Again, the idea of this approximation is that instead of writing, so that's one way to approach that. Well, many of them. So instead of writing this excluded volume integrated with two distribution functions, we say excluded volume is the first term of the virial expansion of the regular correlation function. So why don't we replace this by the correlation function? But we do not know the correlation function, so we need to take it from somewhere. So let us take it from the theory of hard spheres, which is very well developed. So, and then we can take it from the theory of hard spheres, but hard spheres are isotropic, so that's not enough. So we need to make another trick to use this expression. So there is another approximation here, which is a scaling approximation. So we assume that correlation function depends on the ratio of the intermolecular distance and some orientational dependent function, which should depend on the shape. And because of this mathematical form, we can integrate over distance. And now, if we assume that the cube of sigma is the excluded volume, then we recover this Onsager part. But this is the assumption, right? Nobody knows what is sigma. And then we have here the integral of the pure spherical correlation function, which is taken directly from the theory of hard spheres. So you get this result, where this is the packing fraction. And what is important about this, that the functional form is not very important. Qualitatively, it is important that at large densities, this packing entropy should diverge. It should become large. And this is because of this factor, 1/8. But we discussed it already during this workshop with Bob Evans, for example, and he thinks that there are too many approximations here. That's a conventional approach, so we have seen maybe 3 or 4 talks where this has been used. But again, there is no real justification. There are other approaches. For example, the one which Bob Evans tried to describe, where another portion of intuition is used to fight with this integral, with this packing entropy, using curvature of bodies. And I can't say that I can make any comment about that. This looks interesting, and it's a completely different approach. And there may be more. I mean, I'm sure that one can invent plenty of things here, but this is not very well known. Okay, so there were talks about density functional approach, because I only want to say qualitatively that in fact the only systematic way to proceed from Gibbs energies expressed in terms of partition functions, Hamiltonians and external fields to the density functionals is the density functional theory. So it is extremely nice. Formally, the only disadvantage is that you do not know what is in it. Because what you know only is that you split free energy into the ideal gas part and generating functional, which is all the rest, which depends on interactions. And you do not know this generating functional, you know its functional derivatives, which you can derive from general statistical mechanics. Most importantly is that the second derivative is the so-called direct correlation function. And so then you can, in order to make it practical, what people do, they perform functional Taylor expansion of this, of free energy around the isotropic phase. So in the isotropic phase, the distribution function is constant, and then in the, say, nematic phase, it is not constant, and so you expand in the deviation. And this is the ultimate way to derive Landau-Desjardins theories and all coefficients, the most consistent one. Because this difference of distribution functions is easily expressed in terms of order parameters. And so you immediately get all coefficients to any order without any further tricks. And now you see that coefficients generally depend on this C2, and C2 is not a mean field approximation. It's in general contains all correlations which you have in the system. So in principle, you can get in this way very general expressions. The problem is we do not know C2. Another problem is, which maybe Claudio will correct me, but it can't be directly simulated, because it is not a correlation function. That's a direct correlation function. And the full correlation function, which you get in simulations, is related to it by Ornstein-Czernicki equation, which is not so easy to solve. So you need to solve it numerically for anisotropic systems, and so on and so on. So that's just a thing in itself. That's the problem. But what is important, that if we do not know it, but we consider, for example, the system of uniaxial molecules, then again, you see that if we describe nematic phase, these distribution functions are independent on position, so we can just formally integrate it over position, and then our pair correlation function also depends on one angle between two molecules, and we can expand it in Legendre polynomials, and we reduce the free energy to the mean field form mathematically. And that's the reason why it works. So in fact, it is density functional works and not the mean field, because mathematically there is absolutely no difference on the level of second rank polynomials. The only difference is in this constant, which is in the mean field is the average potential, and here it is something which we do not know, which includes everything, all correlations. But mathematically the same thing, so the same order parameters, and provided we map one theory on another formula. Yes, and so now there is what is interesting again about the density functional theory, that you can derive everything from it. So for example, mean field theory corresponds to the following approximation for the direct correlation function. So attraction potential times this step function, which accounts for short range correlations divided by temperature. So Onsager theory, C2 is just step function only. Now, generalized van der Waals theories, this C2 is the sum of two terms. So the hard core, which is determined from spheres, for example, using Parsons-Lee approximation of something else, plus attraction, and so on and so forth. So you can do everything. The only problem is that you can only derive what you already know. So there is no way how you can derive new approximations, and if you try, you are in trouble. And that's one example when you are in trouble. So imagine that you want to use such a nice approximation. You generalize Onsager, simply putting attraction into the exponent. Why not? There should be such term generally, right? And then imagine that you, now for simplicity, for attraction, you take this form, you consider the Lever-Laschel model, so the system on the lattice, and then you see that you make an order of magnitude mistake for the nematic isotropic transition in this way. Because if you take mean field, then the energy is determined by the average of this constant, and mean field may be wrong by a factor of 2 or something like this, maybe, but not by an order of magnitude. And if you estimate the transition temperature from this, using this correlation function, then you see you integrate the exponent here. And the exponent has a strong peak, because this constant J, according to the simulation results, is larger than KT several times. No. And so as a result, you have a strong peak, and you have e to the power 3 or 4 or something like this, which is a significant number. So if you just do not know what to do, and you use this approximation, you immediately get wrong. And there are papers where people are using this, actually. So one should be very careful. That's the message. And so I think that maybe that's enough, right? Because I wanted to say a few words about cluster approximation, but there is no time for that.
Maybe you can squeeze that into your second lecture.
No, yes, because there is one more powerful approximation which enables one to take into account orientational correlations. Because the problem with all these approximations, generalized van der Waals, Onsager, everything, is that they do not account for orientational correlations. And there are cases where they are crucial. For example, you have polar interaction in real systems, dipole-dipole, or just any polar shape. And they do not contribute to the free energy in the mean field approximation at all. They do not contribute in any type of Onsager approximation and generalized van der Waals and everything I have discussed. And I know only one practical approximation where they can be taken into account, and that's cluster approximation, two-particle cluster, but it's badly inconsistent. It's derived only on the lattice. There is no derivation for fluids. So what, for example, people are using is just some kind of interpolation from of the formulas from the lattice theory. But it works. It makes everything better. It's better prediction for the transition temperature, for all other parameters. And in this approximation, you just, consider, so you spoil Hamiltonian in a different way. So you keep interaction between two molecules exactly, and interaction with the rest of the nearest neighbors in the mean field. And then you can increase the number of clusters, if you will. And in this way it works, and it works actually, but the problem is the free energy. The free energy which you get is not a density function. And I do not know how to derive a density function in the cluster approximation. I have not seen this in the literature. And this prevents us from calculating flexi coefficients, elastic constants, and other things. Just impossible at present, even though the effect is huge. So the last thing I will show you, so that's the shift of the uniaxial biaxial transition in bananas. If you take polar interaction into account, polar shape and polar. So that's a significant shift. So in real system, this would be dozens of degrees, maybe hundreds of degrees. So this effect cannot be neglected, and still there is no good way to take it into account. So that's all, and I'm sorry for the delay.
So I suggest we talk to Misha individually. We have some questions, or perhaps over lunch.
Okay.